This is the start of the last unit for the term. It's about chain and product rules, which is all just differentiation rules. We've got 3 topics and it should be done in a week. So I'll go into the first one, which is the chain rule. Quick reminder about differentiation. So process of differentiation finds the gradient of a function at any point, and it's got 3 different representations: f dash of x, dy dx, or y dash. They're all the same, just different notation depending on how the original function is written. Okay, so you need to be familiar with all of the types. And just as a review, let's see if you remember how to differentiate these 3. So pause this and differentiate the 3. Alright, we'll see how you went. So we'll remember the rule for differentiating polynomials. If I've got a polynomial that's kx to the power n, when I differentiate it, I will get kn x to the power n minus 1. In other words, multiply by the power and then reduce the power by 1. Let's do that. I've got f of x, so this one will be f dash of x. 3 times 2, x to the power 2 minus 1, or 6x. Okay, at this point, I'm happy for you just to write the 6x without showing any working. Part B, I've got y equals, so I can choose the y dash or the dy dx notation for my answer. I'll do the first one in dy dx notation. Differentiation of a constant is nothing. So that one's nothing, and differentiation of 5x cubed, 5 times 3 is 15, and x to the power 3 minus 1, which is 2. Final one, I'll use y dash just for fun. I can't differentiate this yet because the variable is on the bottom. So before I use y dash, I'm going to need to rearrange this, bring the x squared up to the top of the fraction line. It'll become 5x to the power minus 2. And now I can differentiate. Y dash is 5 times minus 2, so minus 10. X to the power, reduce this power by 1. It's minus 2 degrees, gets a degree colder, it'll be minus 3 degrees. And if I want, I can put it back into the same notation that it was given. This x to the power minus 3, bring to the bottom of the fraction, make a positive power. Alright, so that's just a review. We're going to look at some more advanced functions, okay? And we need some additional rules. For example, the chain rule. Okay, we'll need this when we do some functions like sine and cosine in the future. But for today, we'll just look at it in some simple context so you get a hang of it. If we were to differentiate this function, y equals 3x plus 1 all squared, without the chain rule, what we would have to do is do expansion first. So I could write this as 2 factors and do FOIL expansion plus 3x plus 1. Can collect these like terms in the middle. Okay, so I've changed something that I don't know how to differentiate. I don't have any rules for this sort of a scenario into 3 terms which I do know how to differentiate. So I'll differentiate that, either y dash or dy dx, up to you. I'll choose dy dx. Differentiate this, 18x plus 6, and differentiating a constant gives nothing. Okay, so we could do that by expansion, but let's have a look at this chain rule idea. So for chain rule, what I'm going to do is I'm going to say let y equal u to the power 2, where u equals 3x plus 1. So all I've done is this part in the middle, the 3x plus 1, I basically crossed it out and replaced it with u and said, oh, by the way, u is 3x plus 1. But we're obviously not going to just scribble over our exam paper. We're going to show some reasonable communication and justification. Okay, I'm trying to find dy dx. The chain rule is basically taking this dy dx fraction. Okay, I could put anything in here. I could put 1 and 1, it'd be all good. I could put 200 and 200 and be all good. But I'm going to put in here du. Okay, the du's can still kind of cancel out. That's not really the proof, but it's good enough for you to remember this idea. Put the du's in the middle, and we've got this relationship. That this derivative that I'm trying to find, dy dx, I can find it if I can find dy du and du dx. Why did I choose du? Because that's the letter that I've got up here. Okay, it won't always be u. You might use m or some other letters. So I'm going to find, first of all, what dy du is. Okay, I'm just going to differentiate this with respect to u, which is 2u. And I'm going to differentiate u with respect to x. So I'm going to find what du dx is. Okay, so differentiate this side, and I get 3. So you really need to know du dx means differentiate u with respect to x. Okay, with respect to. So I've found dy du and I've found du dx. So I can now substitute them both into my chain rule formula. Dy du is 2u, du dx is 3. Okay, so my derivative is 2u times 3, and I can replace this u with 3x plus 1. So it's 2 lots of 3x plus 1 times 3. Okay, that's my derivative, dy dx. Is this the same as what I got up here? Are they the same? Well, let's have a look. I could multiply these two numbers together. 2 times 3 gives me 6. And then I can expand these brackets, 18x plus 6. Oh, it's the same. So what we've shown is that using this idea, replacing this inside function with u, and writing the inside function, differentiating both functions, multiplying them together, we get the same result as we did just by using expansion. Which one's harder at this point? Number 1 or number 2? Definitely number 2 is harder, but we're going to look at some scenarios where you would be absolutely crazy to do option 1, the expansion. Okay, so let's have a look at 3 examples. So this is just the formal chain rule. So if y is a function of u and u is a function of x, then we can use this relationship. So here we had y as a function of u and u as a function of x. So as a function of x means equals something to do with that variable. I'll have a go at this one. I'm going to say let y equal u to the power of 100, where u equals 2x plus 5. I'm going to find the two components I need, dy du and du dx. dy du will be 100 u to the power 99, and du dx will just be 2. Okay. Differentiation of 2x is 2, differentiation of a constant is nothing. So the derivative I'm after, dy dx, equals 100 times u to the power 99 times 2. I can substitute, instead of having u there, because that was just a letter I made up, I'm going to put 2x plus 5 instead. 100 times 2x plus 5 to the power 99 times 2. To neaten this up, I'm going to multiply just the 100 and the 2 together. 200, 2x plus 5 to the power 99. If you try to differentiate this by expansion, yeah, I'll see you later next week once you've finished the 20 pages expansion. Okay, example 2, I'm using the f of x notation. Yeah, it's all good. we'll have the same sort of scenario. I'll change this to y equals. Okay, just leave it as y equals, because our formula is in y equals. You can say y equals f of x. We'll just use y equals. I'll do a similar substitution. Let y equals 3u to the power 8. So this thing that has something else happening to it will make the u function. Okay, where u equals 6x squared plus x. I'll find what dy du is. So differentiate this guy. 3 times 8 is 24 u to the power 7. And I'll find what du dx is. Might be a bit more interesting. 12x plus 1. So by the chain rule, should probably write some comment in here for good CJ. dy dx. And I should probably write the formula as well. Okay, so write the formula the first times you do it, so that you get familiar with it. Dy du is 24 u to the power 7, and du dx is 12x plus 1. Since I'm multiplying everything by 12x plus 1, I need to have brackets in there. I can then replace the u with 6x squared plus x. 24 6x squared plus x 12x plus 1. That is my derivative. And typically we want them in factorized form. I missed the power 7, sorry. That was close. We want them in factorized form. Okay, we don't want them expanded, because we're typically then going to set the derivative equal to 0 to try and find some turning points. Final example, another y equals 1. Okay, so what I'm going to do is choose the inside. It's always the inside function that we make u. So I'm going to have y equals the square root of u, where u equals 4x plus 7. I'll differentiate both of them like normal. This first one, before I differentiate it, I'm going to remember that square root of u is u to the power of a half. Okay, cubed root of u would be u to the power of a third. Fourth root of u would be u to the power of a quarter. Seventh root of u cubed would be u to the power 3 on 7. So whatever this root is, always becomes the bottom of that fraction. Should I make this bigger so that I can, yeah, that's better. So I've changed u into a form where I can differentiate it. Now I can find what dy du is. It'll be a half, and then u to the power of a half minus 1, so power of minus a half. And du dx, I'll differentiate this, it's 4, differentiate this, it's nothing. So my derivative, dy dx, will be dy du times du dx. Slot in the two things. I've got a half u to the power of minus a half times du dx, which is 4. Okay, just putting those two together. That escalated quite quickly. I've got u in my answer. I don't want u's, I want x's, so I'll replace it with 4x plus 7. A half times 4x plus 7 to the power of minus a half times 4. What are we going to do with all these numbers and stuff going on? Okay, this negative a half, never want negative indices in my answers, so this is going to have to go on the bottom of the fraction line. 4x plus 7 to the power of positive a half, and also on the bottom of my fraction line is 2, on the top of my fraction line is 4. I can cancel these two, and I'll be left over with a 2 on the top and instead of this half notation, I want it like I was given in the answer, the square root notation, 4x plus 7. Alright, so from here, do question 1 and 2, the first and second column, and also question 1, the first column. There's 2 question 1s in these questions. Okay, I should probably have renamed them, but I'm sure you guys will figure it out. So basically these guys, these guys, these guys, these guys, and these guys. That's a bit, actually. Alright, well, have fun with them. This video is filmed in Q1.